Okay. So C doesn't really, the standard the library doesn't provide you with any collection classes. All you get are arrays in C. So if you come from a different programming language like Python or Java, where there's a whole bunch of different collection classes for you to use, you're often in the situation when you're programming in C that you really want, or you really miss these classes, or these other collections. So if you want something like an array-based list in C, you've got to roll your own. Or you have to find a library, a third-party library that already implements one. Right? So today, we're going to try to get through the implementation of an array-based list. Right? If you go on the lectures page on OnQ, you will find the source code for today's lecture. Right? So everything's there for you. We're going to implement a dynamically resizable list of int elements. Right? So you're going to see one of the other things that the C language is lacking in this lecture. I'm going to use a few functions that we haven't seen before. Right? They'll make our life a little easier, hopefully. So the documentation for these three functions are also listed here. So if you just hit the links, you'll get to the documentation. I guess I'll quickly tell you what these do. Memcopy copies a chunk of memory into another non-overlapping chunk of memory. Memmove does the same thing, except you can move a chunk of memory onto an overlapping chunk of memory. Okay? And snprintf is like printf, except it will print to a string instead of printing to standard output. And it will only print a limited number of characters to the string. So that's what that N stands for. Right? So it will let you print a specified number of characters to a string. And I'm going to use, so these three might show up today. It depends how quickly I go through this lecture. Okay, so first of all, a quick reminder on what a list is. Right? So you've used these a lot in 121 and 124. Right? A list is a sequence of elements of a single type. So sort of like an array. Right? An array in C is a sequence of elements of a single type. Right? Like an array, the elements have indexes, so position 0, 1, 2, and so on and so on. If you're in Python, you've got negative indexes, which are nice, but I'm not going to implement that today. That would be a nice extension to the source code. So if you're looking for exercises, figure out a way to change my code so that it accepts negative indexes. Okay, the size of the list is the number of elements in the list. Okay, which means there's a concept of an empty list, right? So the empty list has no elements. Now, when you're talking about array-based lists, right, you've got an array that actually holds the elements, right? And so the array also has a size or a capacity, right? So the capacity of a list is the maximum number of elements that you can add, is the maximum number of elements that you can store in the list, right? So the size and capacity are two different things. Right? The size in particular is never bigger than the capacity. In most, well, that's not true. I don't know if you'll ever see the formal abstract data type definition of a list during undergrad. You might not. So there's two ways to define a, well, there's more than two ways to define a list, but there's two common ways of defining a list. One is that when you add an element to the list, it adds to the front of the list. Right? But normally, when you use an array-based list, when you add an element, you add to the end of the list. So that's what I'm going to do today. I'm going to add to the end rather than adding to the front. If you're talking about the theory of data structures, then it doesn't matter where you add. Right? Theoretically, they have the same performance. In practice, they don't. Okay, so when you add an element to the list, obviously that increases the size of the list by 1. It does not change the capacity, though. Right? Unless your list happens to be a type of list that automatically increases its capacity when it's full. Right? So if you have a list with capacity 5 and you have 5 elements in the list, so a list with capacity 5 and size 5, if you try to add something to that list, it would be nice if that list expanded its capacity. Right? And that's exactly what the Java and Python versions of lists do. Right? And that's what we're going to do today as well. Right? So that's going to free us from the constraints of a C array. Right, where once you make an array, you're stuck with the number of you're stuck with that array, right? So you can't easily expand the size of that array. Well, you can't expand the size of the array automatically. All right, so here's an empty list with capacity 8. Right? That's how I'm going to draw it. I'm not actually going to show you the elements, so I'm not going to put anything into the boxes. Right? So that has capacity 8, so they're all empty boxes. Are there any valid indexes? The answer is no. Right? If you try to do anything with this list, like get element 0 or 1 or 2 or 3, right? Those should all, those are all undefined behavior for this list. Right? In Java and Python, you get an exception of some kind. Right? What you get in C, well, who knows? We'll see. Right? If I add an element, that adds to the end of the list. Right? So the end of the empty list is the front of the list. So when I put one element in, right, I get this element at the front. Right? So I now have capacity 8, size 1, one valid index, right? Index 0. Right? Add another element, I have size 2, 2 valid indexes, right? 3, 3 valid indexes. If I add 5 more, right, I have a list of size 8, right? Which is the same as its capacity. Right? And what are the valid indexes? Well, they're from 0 to size minus 1. Right? This is all, you all know this, right? Okay. Getting or setting an element. So in a list, like an array, you can get or set an element by its index. Right? So if I want to get or set the element at index 3, right, that will either return the value at index 3, or it will change the value at index 3. Right? So the one in yellow. Right? Now, it's undefined behavior if you try to get or set an element with an invalid index. Right? So even though this is an array-based list and you can access array element, or the array element at index 3, if you try to do this with a list, you get undefined behavior. Right? So if you get the value from that index, something bad might happen. Right? Or if you try to set the element there, something bad might happen. Right? Or nothing might happen, or maybe the element will be set or get the way you might expect it to be, because it's just an array after all. Right? But we're going to say that that's undefined behavior. Right? Python and Java will say it's defined behavior and it's an error. Right? We're actually going to try to replicate that behavior, that type of behavior today. Okay, so what happens when you add to a full list? Right, so here's a full list. I want this list to be dynamically resizable. Right? So when I call some function that adds an element to the list automatically expands so that I can add more elements. Right? So what does that mean? Well, it means I have to increase the capacity of the array. Right? It doesn't mean I just have to increase the capacity of the array. Right? I have to increase the capacity and then copy over all of the elements. Right? Because you can't, you're not always, because arrays aren't technically resizable in C. Right? There is that realloc function, right, which sometimes can reallocate a new array in the same place. Right? But technically, you have to copy the existing elements into the newly expanded array. Right? Now, how big do you make the new array? Right? So if you add one element, you've got several choices. Right? You can either increase the capacity by 1. Right? You can increase it by some other constant value, so you can always increase it by, say, 10. Right? Or you can increase it by some multiple of the current capacity. Right? And if you do a complexity analysis of what happens in each of those cases, right, you'll quickly realize that you want to increase the capacity by a multiple of the current capacity. If you increase the array capacity by 1, or by a constant amount every time, then it turns out your add function has complexity big O(n), which you don't want in a list. Right? This is basically an array. You ought to be able to put something into an array with complexity big O1. Right? It turns out if you expand the capacity by a multiple, then you have what's called amortized big O1 complexity. Right? That is on average, right? On average after performing many add operations, on average, the complexity is big O1. Right? You might learn about amortized complexity analysis in CISC235. You might not. Right? Normally, that's something you do in a second data structures or algorithms course. OK, so we're going to double the capacity each time. I think the Java implementation of ArrayList is it multiplies the capacity by 1.5 every time. Right? It doesn't matter what you do. Well, I mean, You don't want to make it too big, so you don't want to increase the capacity by a factor of 10, because then you end up using up a lot of memory that you don't need. Right? You don't want to make it too small, because then your average performance becomes worse. Okay, once you increase the capacity of the array, so I've doubled the capacity, you just go ahead and insert the element at the end of the list, right? Which we already know how to do. Okay, now what happens if I insert at a particular index in the list, right? So I want to insert somewhere in the middle, or perhaps the end of the list. Right? So here I want to insert at element 4. Right? So to insert into a list, you need to make room for the new element. Right? You don't want to overwrite the element at index 4. Right? That would be setting the element at index 4. I want to insert into the list. So what that means is I want to take element 4, 5, 6, 7, and 8 and move them all over one position to the right. Right? So in other words, I want to take these elements and shift them to the right by 1. Right? And that gives me space to insert the new element. Right? So that's what we're going to have to do when we implement insert. Right? Now, insertion is a bit weird, because many implementations of lists let you insert using an index at the end of the list. Right? So for example, I can insert at element 10 of this list, even though element 10, or index 10, sorry, is not a valid index. Right? So this is a little bit unusual, because the index is not technically valid, but most list implementations allow this. Right? So you can insert at the element past the current end of the list. Right? And we're going to do that as well. Right? But that's easy to implement as well. Right? You just check what the index is, compare it to the size. If it's equal to the size, just call add. Right? And that puts it at the end of the list. Okay, now how about removing an element by index? Right, so here I want to remove the element sitting at index 4. Right? Most implementations of remove return the removed element back to the caller. Right? So what do I have to do? Well, I have to take elements. When I get rid of that element, I don't want a blank spot in this array. Right? Because lists are supposed to be contiguous sequence, or it's supposed to be a sequence of elements. Right? So if I take something out of element 4, I need to shuffle everything over to the left by 1. Right? So in other words, I have to take elements 5, 6, 7, 8, 9, and 10 and move those over. Right? But before I do that, I need to make a copy of the element at index 4, because I have to return that back to the caller. Right? So copy element 4, and then move everything in red one position to the left, right? Which decreases the size of the list by 1. Okay, so we're going to implement all of those methods, functions, hopefully today. All right, now, how am I going to check, or what am I going to do when an index is invalid? Right? So what I'm going to do is I'm going to use the assert macro. Right? So I'm going to include this header file assert.h, which is one of the C standard library header files. Right? That provides what's called a macro to me. Right? So a macro is just a fragment of code that happens to have a name. So it sort of looks like a function. It's not really a function. It sort of looks like a function. Right? So it's just a piece of code. It has a name. In this case, it's called assert. Right? So when you use a macro, the preprocessor takes the code that corresponds to the name and pastes it into your file. Right? So it's the job of the preprocessor to take macros and stick them into your program wherever you use them. Right? The assert macro looks like this. Right? So you assert, round brackets, some condition. Right? So that condition is either true or false. Right? If the condition is true, nothing happens. Right? Your program keeps on running. If the condition is false, your program terminates. So it stops prematurely. Right? So it doesn't exit via the normal exit mechanism of C. Right? Program stops as though it crashed. Right? And then some error exit status is set. Okay? Now, the nice thing about assertions is you can disable them via a command line option. So when you're debugging, you can put asserts into your code. Right? The assert statements hopefully help you find out where the errors in your code are. Right? When you release your code when you release your code to the public, right? In other words, when you publish your product, right? You disable the assertions via the compiler, right? And now these conditions are no longer checked, right? So in other words, they disappear from your code, which means you don't pay the price of checking by checking the condition every time you call a function. Right? Now that's both a blessing and a curse. right? So it's nice because when you run your program, you don't have to pay the price of checking the assertions, right? It's bad because if there's some bugs you haven't found yet, the assertions aren't there anymore to help you, right? So now something strange happens in your program, and then you have to deal with customers complaining. Okay, so that's actually it for the PowerPoint, I think. Yes. So let's go and look at the source code now. All right, so okay, so this is the header file for the list type. Okay, so first thing in your header file, you've got the include yards. Right? The include yards are there to make sure that this header file is not inserted into another source code file more than once. Right? I'm going to include standard bool so that I can use the type bool, little b bool, so for true and false. Right? And now there's the first, on line 9, there's something we haven't really seen yet. So on line 9, there's a type def of a structure. So I'm saying there's some structure called list. Right? So that's what struct list means. Right? I've got a type def, right? So I'm saying that the word list means the type struct list. Right? But notice what's missing here. The definition of the structure is missing. So it's not actually here. Right? The definition of the structure is going to be somewhere else. Right? And so what this does is that it hides the implementation of my list class, of my array list, from anybody that's using it. Right? Because anybody that's using it is only going to get the header file. They're not going to get the corresponding C source code file. Right? So normally when you distribute a library, you don't distribute the source code for the library. You distribute the header files and the compiled version of the files. Right? So without doing any extra work, an ordinary user can't tell what's inside of the can't tell what's inside the structure. Right? So this is the C way of hiding an implementation from a user. Right? So this is sort of like making things private in a class. Right? No one can actually see, another class can't actually see what's in this class. Right? So here in C, an average user cannot see how this list class is implemented. Right? All that they know is that there's some type called list. Right? So the definition of the list structure is actually inside the list.c source code file. So we'll take a look at that in a second. All right, now, there's no standard documentation format for C. Okay? So people are free to document their code however they want. Right? So here I'm taking a very free-form approach to documenting the code. Right? Some people will basically use something that looks like JavaDoc. Right? So they'll have @param, @return, right, and stuff like that. They'll document all the parameters and all the return values. So here I'm going to do something similar, but I'm going to put everything as text in a comment above the methods. Right? So it's less formal than JavaDoc, but it's still complete. Right? There's no standard format for doing this. And C doesn't have a tool like JavaDoc for generating generating documentation from comments. Right? You have to use a third-party tool to do something like that. Okay, so this is the analog of a list constructor in Java. Right? So I have a function called list_init_empty. Now notice that all of my functions are going to be prefixed with the word list. Right? So that's another one of the consequences of using C. Right? And so in C, you can't have two functions with the same name. Right? So I don't want to make a function called init or just plain old init because that's probably a very common function name. Right? So here I need to use function names that are specific to my list class here. Right? So I'm going to precede everything with list underscore. And even this isn't good because if I make a linked list, now I'm going to have to call that something different. Right? So list_init_empty, that makes an empty list. Right? It returns a pointer to the list. Right? Now you can return a list object. That would actually work in this case. But the usual thing to do in C is to return a pointer to the object. And that way people just pass around pointers to objects. Right? If you have to pass around if I pass around a list, I have to pass around everything that's in the structure. Right? So if there's a lot of things that are in the structure, that costs more time and memory to pass those things around. Right? Whereas passing a pointer, I just pass a pointer. Right? So it's very common to see data structure like types everything's done via a pointer. Right, so that'll return a pointer to an empty list. Right, here's another constructor-like function. Right, this initializes a list with a given capacity. Right, it doesn't put anything into the list. It just makes an empty list, but now it has a guaranteed capacity. Right, notice that in the comments, there's always something saying that the return list must be freed. Right, and I have a function that will free the list. Okay, what else do I want to do? Well, that's like a copy constructor in C. That's like a copy constructor in Java. Right, so list copy gives you back a new list. That's a copy of an existing list. Right, so it's an independent copy, meaning it has its own array and it has its own copy of the elements in the array. All right, size. Whoever's using the list is probably going to want to know how many elements are in the list. Right, so I'm going to provide a method called size, or list size. I just realized that there's a function missing. There should be one that tells you whether or not a list is empty, because that stops you from having to call size and checking if it's equal to 0. Right, so there should be another function in here called list is empty, but there isn't. Okay, let's see. Let me back up a second here. For copy, you're going to pass in another list. Right, so you're going to pass in a pointer to another list. Right, notice that the pointer, or the parameter is marked const. Right, so that means list copy cannot change the other list. Right? So if you try to change the other list inside list copy, the compiler will complain. Right? So what this function is saying is it's going to make a copy of another list, and it promises not to modify the other list, right? Which is nice. Right? Size. The parameter is also marked const. Right? So what does that mean? It means, well, when you ask for the size of the list, I'm not going to change the list. Right? That's also nice. Okay, here's get. So get's going to return an element in the list. Right? So I have a list of int, so it's going to return an int. Right? It takes a list by pointer again, and also const. Right? So again, get's not going to change the list. Right? And it will return the element sitting at that index. Right? Using an invalid index produces undefined behavior. Right? So it's warning you. You have to be careful that you have to be careful that the index is always valid. Okay. Set is the same as get, right? Except the list is no longer const. Right? Can't be const because I'm going to change an element inside the list, so I'm going to modify the list. Right? Therefore, the list that list structure can't be const. Right? Right? So when you look at this function and you look at the get function, right, you can tell right away the get function has no side effects on the list. Right? When you look at set, right, you can see, oh, there's probably going to be a side effect of some kind, right? Meaning that the list is going to be modified. Okay, what about add? So add adds an element to the end of a list, right? If I'm going to modify the list, it can't be const. This will return true if we successfully add to the end of the list, right? It will return false if we couldn't add to the end of the list, right? When will it return false? Well, it will return false if I try to allocate some memory to expand the list, but there isn't enough memory. But the allocator couldn't return, could not perform the allocation, right? So if you run out of memory, add's going to return false. And that's the only time it should return false. Okay, so here's insert. Insert's similar. It will return true if we successfully insert that element into that list at that index. Right? Insert has to return true or false too, because when you insert into a list, you might have to expand the capacity of the list. Right? So if you insert into a full list, you have to expand the capacity. Right? Expanding the capacity may not work, right? In which case you should return false. Remove removes the element at that index. Right? Again, the list is passed in, it's not const, right? Because I have to modify the list. And it returns the element that was removed. Okay, finally, I've got two versions of the toString method function. Right? So these are the analogs of toString in Java. Right? Now, both of them take in a list that's const, right? Because toString should not modify the list if you're going to generate the string representation of a list, right? The first version of toString actually returns a char array, right? So it tries to return a C-style string back to the caller, right? The second version does not. The second version asks the caller to provide an array that the function can put the string into, right? So that's buff, right? So this version of toString is going to use an array provided by the caller, right? So that's going to use that for the storage of the string, right? Now, if you're passing in a pointer, the function needs to know how much space is in that buffer, right? So the caller has to provide the buffer size as well, right? And then finally, this version of toString returns the number of characters that it puts into the buffer, right? So the idea in the second version of toString is someone gives you a buffer big enough to hold the string representation of the list, right? If it's not big enough, right, this function is actually very nice. So if it's not big enough, this function fills up the buffer as far as it can and then returns back the number of characters it put into that buffer. It always returns the number of characters it put into the buffer. So if someone passes you the function a buffer of size 1,000 and the list has no elements in it, right? It turns out this version of toString puts that into the buffer, right? So just like Java's or Python's toString method, right? So it'll tell you it'll tell the caller that it put 2 characters into the buffer, right? Okay. Finally, there's a function to free the list. Right, so if this is the function that the caller has to use when they're done with the list so that they can free the memory that's allocated to the list, right? They can't just free the pointer because they don't know what's inside the structure, right? So if the structure has something else in it that's dynamically allocated, right, that other thing has to also be freed, right? But they don't know what's in it because all they have, all they have is this, right? So they don't actually know what's in the structure, right? Which is why they have to call the list free function to free all the memory allocated to the structure, right? Only the list implementation knows what's inside the actual structure. All right, anybody have any questions? Anybody? All right, here we go. Here's list.c, right? So I've got a bunch of includes, so it turns out I need quite a few of them. Right, I need assert because that's how I'm going to check for valid indexes, right? You might wonder why I need limits, but you'll see that probably next day because it looks like I'm not going to get to it. So remember, limits are the integer limits, right? The minimum and maximum values. I need standard def for I don't remember what. Well, we'll find out shortly. I need standard I/O to do any printing. So anything that involves printing to a string or printing to standard output, I need standard I/O. I need string. So we haven't seen this class yet, but this header file yet. But we're going to see it next week when we talk about strings properly. Right now, I'm just sort of saying a string's an array. It's got a null terminator. Right? But there's a whole bunch of functions that are dedicated to operating on strings. And I need my header file. Right? Because my header file is the one that declares all of the functions that are supposed to be in this source code file. Right? Okay, so the first thing I'm going to do is I'm now going to define my structure. Right? So here's where I define, here's where I define the list structure. Right? The type def in the header file, right, that just says there's something called struct list. Right? At some point in time, I have to actually say what struct list is. So here's where you say what it is. Right? So what's in a list? Right? Well, I have the array that stores the elements. Right? So there's my array. Right? It's just a pointer it's just an int pointer. Right? I need to know how big is that array or what is its capacity. Right? So I have to store that. Right? And then I need to know how many elements are currently in the list. So I have to store that as well. Right? I'm using size t here, size type, because it's an unsigned value. Right? Which is nice because I never have to worry about indexes being negative in this case, right? If you use size t, right? Because they're unsigned. So I only have to check for the upper bound on my indexes. Okay, carrying on. The default capacity is a constant. So it's going to be the default capacity of the arrays that I make. Right? So when I make an empty list using init empty, I'm going to make an array whose capacity is size 4. Right? That's actually a little small. So the Java implementation uses a default size of 16, I think. I don't know what Python does. Right? But normally when you make a list, you make an array that's bigger than 4. Here I'm going to use 4 because when I print out the list, I want to show you that it actually dynamically resizes properly. Right? Okay. And then I've got a separate function here, right, that's hidden inside the source code file. Right? So the people people who are using just the header file, they don't know that this function exists. Right? But the function exists inside of this file. Right? So the function here is add capacity. So that's the function that's going to expand the size of the array when needed. All right. Okay, so here's init empty, and here's init, which initializes to a given capacity. Right? So for init empty, I'm just going to call the second function and pass in the default capacity. Right? That avoids duplicating code. Right? You could duplicate the code here, but if you don't have to, don't do it. Right? So init does everything init empty has to do. Right? So I'm just going to use init empty. I'm just going to use init to implement init empty. All right. So what does this do? It makes a list. Right? So it makes a list structure. Right? It's going to return a pointer to that structure, and it also has to allocate the underlying array. Right? So there's where I dynamically allocate my list structure. Right? So you use malloc, right, to allocate enough memory for a list. Right? So you use size of list to find out how much memory every list structure takes. Right? That's unallocated memory. Right? So malloc is uninitialized memory. So now I have to go in and fill in the fields of my structure. Right? So I have to specify the capacity, the size, and I have to do something with that pointer to the array. Sorry, I have to do something with that pointer. All right. So that makes the array. Right? So that allocates memory for the array. Right? Again, I'm using malloc. Right? So uninitialized memory. How much memory do I need? I need that much memory for the array. Right? But you have to multiply it by the size of int. Oops, sorry. But you have to multiply it by the size of int. Right? So that gives me enough memory to hold capacity ints. Okay. Malloc can fail. Right? So if malloc fails to allocate any memory, it returns null. Right? So you have to check the result of calling malloc. Right? So I'm going to check, is the array null? Right? If it's null, failed. Right? So I'm going to return a null pointer. Right? So now the caller also has to check, right? When they call list init, do they have a null pointer? Right? Because if they do, then it couldn't allocate the list. Right? Now I should point out that this is only going to happen when you run out of memory, right? Which on a modern computer hopefully doesn't happen. Right? But if you're writing an application that really uses up a ton of memory, then this might happen. Right? Okay, so I've allocated the structure. I've allocated the array inside the structure. Oh, sorry, I've allocated the array. Now I have to set the fields or the elements of the structure. Right? So this is like calling a constructor in Java. Right? If you imagine that ARR, capacity, and size are fields of an object, well, I have to initialize all those in the constructor. Right? Now remember, T is a pointer, so I use the arrow notation to access the elements of the structure. Right? So the array in the structure, I just make that point to the array I allocated. Right? The capacity of the list structure is just the capacity that was passed in. Right? And then the size is 0. Right? So I have an empty list. This works. Right. I don't have to validate the capacity either. Right? The size T is unsigned. Right? So no, the smallest size it can be is 0. Right? And I think you are allowed to malloc a memory of size 0. Right? So that will always, this should always work. I didn't actually try it. I guess I should try it. I didn't actually test it. Right? So there are your two init functions. So copy is like a copy constructor in Java. Right? I want to copy another list. Right? So how do you copy another list? Well, I'm going to copy a list and I'm going to return a new list. Right? So I have to allocate space for that list. Right? So there's where I allocate space for the list. Right? Now I need to copy everything that's in the other list. Right? So I'm going to allocate an array. Right? That's the same capacity as the other list. Right? That has the same capacity as the other list. Right? So inside this source, so remember, C doesn't have any notion of public, private, protected, or package private. Right? Anything that's in that structure I can access inside this file. Right? So I can just write other capacity without any issues. Right? There's no access modifiers in C. Right? So I can just write other capacity. Right? That's the capacity of the other list. And then I multiply it by the size of int to get enough memory. Right? I check. Right? Is that array null? If it is, then this copy function failed. Right? If it's not null, it succeeded. So now I want to copy all the memory that's sitting in that other array into this array. Right? Well, I don't want to copy everything. I only need to copy the elements that are sitting in the other array. Right? Now you could do this with a loop, right? Because you've got two arrays. Right? So you could write a loop starting at 0, going up to but not including the size of the other list. Right? And then copy in element 0 from that array into element 0 of this array. Right? Element 1 of the other array into element 1 of this array, and so on and so on. Right? C, however, has a function called memcopy, which will just copy a chunk of memory for you. It's very fast. Right? So it's, if you write a loop to copy the elements individually, depending on your compiler settings, the compiler might turn that into a memcopy anyway. Right? So memcopy, that's the destination, right? So that's where it should copy the contents into, right? So that's destination, right? That's the source, right? So I'm going to copy the elements from the other array into T's array, right? Now, memcopy takes in the size of the memory block that you want to copy, and the size is defined in terms of the size of car, right? So units of 1. Right? So I want to copy in that many elements, right? So the number of elements in the other list, right, times the size of int, right? Because all the elements in the other list are ints. Right? And that will copy everything in the other array into this array. Right? And it'll do so very quickly. Okay, so once I've done that, I want to copy over. Oh, hey, that's a mistake. Well, that's funny. That's other capacity. And that's other capacity. I never actually tested this function, so those are wrong. Capacity equals, sorry, other capacity. There we go. Okay, so the capacity of T is the capacity of other, and the size of T is the size of other. Right? And now you can return the pointer to the list. All right, any questions so far? Okay. The size of the list is easy because I've got a member in the structure that represents the size, right? So I can just return T size. Get is also easy, right? Because I'm just getting an element in an array, right? So if the index is valid, I can just write that, right? And that's very fast, right? So in C, so for any array, that's O1, right? Big O1, right? Now, I'm going to use assert to make sure that that index that's passed in is actually valid, right? So again, I don't have to check if the index is negative, right? Because it's unsigned, right? That's unsigned, so I'm never worried about the index being negative, right? But what I am worried about is that the index is equal to the size or greater, right? So I want to assert that the index is in fact less than the size of the list, right? If asserts are turned on in the compiler, then this will cause the program to stop, if you call get with an invalid index. Right. Okay, now what about set? Well, set's the exact same thing, right? I want to set an element in an array somewhere, right? But I want to return the element that I'm overwriting. Right? So again, use assert to check the index. Right? Remember what's currently sitting at that index in the array. Right? Overwrite what's sitting in the array at that index, and then return the value that you remembered. Right? So that returns the overwritten value, which is nice, right? So if someone wants to set an element in the list, right, they might want the element that they just overwrote. Right? So we can return it to them. Okay, now before I do add, I need a way to increase the capacity of an existing array. Right? Now, last class I showed you realloc, so you can kind of guess that this is going to be realloc. Right? So I want to add capacity to that list. Right? And my the strategy I'm going to use is I'm going to double the capacity of the existing list. Right? So how do you double the capacity of an array? Well, you call realloc. Right? What do you pass to realloc? Right? The array that you want to reallocate, right? And the new size, or the new capacity of the array. Right? So what's the new capacity of the array? Well, it's just twice the old capacity. Right? So 2 times the current capacity. Don't forget to multiply by the size of int, right? Because everything in C is measured in terms of the size of car. Right? So that's pretty easy, right? But you have to remember that realloc can fail, right? If realloc can't get enough memory, or it can't reallocate the memory, right, it returns null. So you have to check, right? Is the newly allocated array null? Right? If it is, I'm going to return false, right, indicating that I was not able to reallocate that array. Right? If you get past this if statement, so in other words, if new array is a valid pointer, well, I've got a new array, right? And I've also copied over all the elements, right? Because that's what realloc does. Right? Realloc also copies the existing elements. Right. So what's my capacity of the new list? What's my new capacity of the list? Well, it's just 2 times the old capacity. Right? What's my new array? Well, it's just new array. Right? If you get to this point in time, if you get to this point in the function, you've succeeded, so you can return true. Okay, now that I've got add capacity, add is not so bad to implement. Right? So for add, I want to add that element to the end of that list. Right? So what do I have to check first? I have to check, is there space in this array, is there space in the array to put the new element? Right? How could I check that? Well, if the size is equal to the capacity, right, you're out of space. The list is full. Right? So call my add capacity function, right? Check the return value, right? If that failed, I have to return false, meaning I can't add another element to this list, right? If it succeeds, well, I just go ahead and add the element, right? So what do I do? Well, I just set the element at t size to be equal to the element, right? And then, don't forget this one. This is the easy one to forget. Right? It's easy to forget to increase the size of the list by 1. Right? But I just put a new element in, so I have to increase the size by 1. Right? And then when you're done that, you can return true. All right, are there any questions so far? Okay. This is exactly what Java's array list and Python's list does, by the way. Right? So when you actually are using those classes, every time you call add or something like that, all of this is happening. Right? Those languages hide it from you. When you actually go to do this in C, you realize what's actually happening. Right? Now what about insert? So insert's a little bit long. Right? So it looks like inserting an element into a list is a little bit tricky. Right? Now remember, when you insert an element into a list, you got to move stuff over 1 position to the right. Right? Okay, so step 1, check if the index is valid. Now you have to be careful when you do this check. Right? Because you are allowed to insert at the end of the list. Right? So that assert statement is different than that assert statement. Right? So when you set or get an element, you want to make sure that the index is less than the size of the list. When you insert an element, right, the index is allowed to be equal to the size of the list. Right? If it's equal to the size of the list, right, that means you're trying to add to the end of the list. So don't repeat yourself, just call the add method or function. Sorry, I teach 124 at the same time, so I always get function and method mixed up. Right? Just call the add function, right, and you're done. Okay, now what happens if you're not inserting at the end of the list? Right? Well, now I have to check, is there space in the array to add the element or to insert the element? Right? So same check here. Right? If the size is equal to the capacity, right, I'm out of space, so add capacity. Right? All right, now what do I need to do? Okay, so I know that I can put the element into the array. Right? Now I have to move a bunch of elements over to the right. Right? So how many elements do I need to move? Right? So I need to move all elements from the given index and beyond, one position to the right. Right? So how many elements is that? Well, that's the size of the array minus the index. Right? How do you get that number? Well, if the index is the size of the array, then you're adding at the end. Right? So you don't have to move anything, so that should be 0. Right? So if index is equal to the size, that's 0. Right? If you're adding at the element that's at the end of the list, right, then the index is size minus 1. Right? How many elements do you have to move over? Well, 1. So size minus 1 is 1. Right? So that's right. Right? So that's how you get n. That's the number of elements I need to move. Right? And now I need to move possibly one or more elements over to the right. You could write a loop. Right? But the C standard library has a function that will move memory for you. Right? So memmove will move a block of memory into another block of memory that's possibly overlapping. Right? So you can move a block of elements in an array into the same array with memmove. Right? How does it work? Okay. So what is this thing here? So t index plus, so that's the array starting at index plus 1. Right? So this is the source. Right? So this is where I'm going to start moving from. Right? That's where I'm going to start moving from. It actually needs an address. Right? So it needs a pointer. Right? So t array index plus 1, if I'm using the square brackets, right, that's returning the element at index plus 1. I need its address. Right? You don't have to use the address operator here. If you use pointer arithmetic, you can just write t array plus index plus 1. Right? And then you don't need to use the address of operator. I think it's a little clearer here if you use the address of operator. Right? So that's where you're moving from. Right? Sorry, moving to. That's the destination. That's where you're moving to. Right? Because I'm moving everything over to the right one. Right? That's where you're moving from. Right? So everything starting at index, I'm going to move over one element to the right. Right? And that is how much memory you're moving. Right? So I'm moving n elements, but each element takes up the size of an int. So that's the number of elements I'm moving over. Right? When memmove is finished, all the elements are shifted over by 1. So I can now simply insert the element, right, at the given index. So you just set the element at the given index, right? And then don't forget to increase the size by 1 because you just added an element into the list. Right? And then return true. So this one actually never, it does return false. It returns false if it can't allocate space for the extra element. Okay, we're out of time, so I will continue with remove and toString tomorrow.